go, rational exponents and radicals. So to get started, let's start off with some definitions. So starting off with the nth root of a. So this is in reference to this image over here, where we have your n, so your number root, we call the index. This is our root, or our radical symbol. And then we have what we're taking the root of, which is referred to as the radicand. So when we're referring to the nth root of a, so this time the nth root of a refers to the number of times n, so n referencing that number of times a root is multiplied to get the radicand. So when we're thinking about like a third root, you're thinking what times itself 3 times gets us to a. The radical here is just a symbol that means nth root. So depending on what you have up there for n, that's your number root. And then lastly, the index of a radical we call the value you want to take the root of. Okay. Next. A radical expression is an expression that contains a radical. An expression involving a radical with index n is in simplest form when these 3 conditions are met. So the focus for today, at least one part of that focus, is on simplifying radicals. And to simplify, it means no radicands have perfect nth powers as factors other than 1. No radicands, so thing under the root, contains fractions, and no radicals appear in the denominator of a fraction. So you cannot have something like the square root of 3 in the bottom. Nothing in the denominator. So our goal here is to start doing some simplifying with roots, with radicals. So let's look at what we call the product property of square roots. So with the square root of 108, the product property refers to pulling out or any factors that are perfect squares. So if we think about like perfect squares, so like 1 is a perfect square since 1 squared is 1. 4 is a perfect square since 2 squared is 4. 9 is a perfect square since 3 squared is 9. So anything that's squared, that's what we consider a perfect square. So we think, are there any perfect squares that factor out of 108? Well, we can start small with 4. So 4 times 27 is 108. And we know the square root of 4 is 2. Zoom in for you. In addition to that, 27, 9 is a factor of 27. 9 times 3 is 27, so this will factor into the square root of 9 and the square root of 3. 2 times 3 here, because the square root of 9 is 3, so we get 6 root 3. Okay. Let's look at number 2. So again, we're looking for those perfect squares. If you can start with the largest possible perfect square, that'll reduce the number of steps. So I'm noticing 4 would work. But what about like 16? 16 times 5 will get us to 80. So 16 is a good place to start. Square root of 16 is 4. 4 root 5. That negative just stays on there. Okay. All right, now we've got some variables. So the square root of 9x squared. So again, what we could do is we can separate this into the square root of 9 times the square root of x squared. Square root of 9 we know is 3. And a square root and square, those will cancel. So we just get x. Okay. Lastly, our fourth example, square root of 75 n to the fifth. Here we have, so 75 will factor into 25 and 3. And then we have that n to the fifth. And we'll talk about that. So 25, square root of 25 is 5, so we've got 5 root 3. As we look at this n to the fifth, so what we can do here, so remember how the square root of anything squared, that cancels it. So what we could do is we could factor this out into the square root of n squared times the square root of n squared times the square root of n. Because when you're multiplying, remember you add the exponents, so 2 plus 2 plus 1 gives us 5. And now we have the square root of n squared is n, square root of n squared again is n, and then we have the square root of 3 times the square root of n, or the square root of 3n. And then n times n gives us n squared. So we've got 5n squared root of 3n. So you want to pull out as much as you can out of that square root as possible. Okay. So this is the product property. The property basically just states if you have the square root of ab, that can be written as the square root of a times the square root of b. So if you can factor out square roots. The quotient property, very similar. This just says you can split up the square roots, or you can split up a fraction into 2 square roots. So essentially we can rewrite this as the square root of 15 over the square root of 64. To which we know the square root of 64 is 8, since 8 squared is 64. Root 15 does not simplify at all, so we stop there. Okay, continuing. And from here, again, you can separate. Put that square root on the numerator, square root on the denominator. Now with square root of 81 is 9. Square root of x squared is x. Same idea here. Square root of x squared over square root of 100. Square root of x squared, those will cancel, so we just have x. Square root of 100, well, that is 10. Sorry about that. Okay. All right. Our last thing here, in terms of properties, is just thinking about cube roots. So remember, for cube roots, you're looking for what cubed gives me this value, or what type of factors are perfect cubes. So as we think about perfect cubes, 1 cubed is 1, so 1 would be a perfect cube, obviously. 2 cubed is 8, so 8 we consider a perfect cube. 3 cubed would be 27, so we consider 27 a perfect cube. 4 cubed is 64, so we consider that a perfect cube. In addition to that, you can think about negative numbers as perfect cubes. So, like negative 4 cubed, well, that would be negative 64, since a negative times a negative is positive times another negative would make it negative. So you may remember with square roots, you can't have negatives, but if you have an odd number root, like 3, negatives inside the square root can actually be okay. And this last one here will apply up here, because negative 64, or we can rather factor negative 128 into negative 64 times the cube root of 2, since negative 64 times 2 is negative 128. And since negative 4 cubed is negative 64, the cube root of negative 64 is, well, negative 4. And we just have that times the cube root of 2. So make sure you have that cube root applying still. It's got to stick with that too. It doesn't change to a square root or anything. Okay. All right, let's move on to the next one. So 125. That makes me wonder, is 5 cubed 125. 5 times 5 is 25, times 5 is 125. So that's good. So let's separate this using our product property into the cube root of 125 and the cube root of x to the 7th. So cube root of 125 is 5. Cube root of x to the 7th. Well, let's try and cancel things. So we can separate that into the cube root of x cubed times the cube root of x cubed times the cube root of x. So 7x's, 3 plus 3 is 6, plus 1 is 7. And the cube roots will cancel cubes just like square roots cancel squares. So we'll have 5 times x times the cube root of x, or 5x squared, cube root of x. All right, let's continue. Here we have a quotient. So let's separate top and bottom. Notice again that cube root's got to stick with it. So as we look at 216, so 5 cubed gets us 125. 216, well, is that, so 6 times 6 is 36, times 6 does give us 216. So cube root of 216 would be 6. Cube root of y, nothing to simplify there. Okay. And the last one here, just continuing with these rational exponents. So we've got some quotient stuff here, so let's start by separating the top and bottom. We've got product stuff between the two. So up top we've got the cube root of 8 times the cube root of x to the 4th. Down below we have the cube root of 27 times the cube root of y to the 3rd. So the cube root of 8, well that's 2, since 2 cubed is 8. Here we can separate that into x cubed and just x, keeping that cube root with it. Cube root of 27 is 3, since 3 cubed is 27, and then a cube root and y cubed will cancel for just y. Up here, we have, these will cancel, so we just have 2x times the cube root of x over 3y. Okay. All right. Got a few more things to touch on here. So remember, we can also consider these in terms of conversions between radical form and exponential form. And it's important to remember that you can have multiple options for your roots, both positive and negative solutions sometimes. So for example, whenever your n is odd, meaning like for example, n is 3, so you'd have the cube root of negative 125, n referring to that nth root, you're always just going to have one solution. So the cube root of negative 125 is negative 5, since negative 5 cubed is negative 125. Same with over here, like if we have, let's make this a fifth root. If we have the 32 to the power of 1 over 5, remember converting to exponential form. Remember it's power over number root. So this is the same as the cube, or the fifth root of 32, which is 2, since 2 to the 5th is 32. So whenever you have an odd root, you can only have one solution. Like here, negative 2 wouldn't work, because negative 2 to the 5th gives me a negative 32. Whereas if you have an even root, then you always have 2 possible solutions. So like here, if we have the 4th root of 16, notice both 2 to the 4th is 16, but so is negative 2 to the 4th. So our solution would be both positive and negative 2. Same follows over here. So we have 10,000 to the power of 1/2. So remember, number, or power over number root. A 2 root is just a square root. And here, so 10,000, the square root of that would be positive or negative 100, since negative 100 squared will give us 10,000 as well as positive 100. So that's something that's important to keep in mind as you're going through some of these problems. If you have cases where your a value, so what you're taking the square root of, is 0, so like for example here, if we have an 18th root of 0, that's just 0. Any root of 0 is always just 0. There are some cases as well where, and we're going to ignore this problem, there are some cases as well where your a value, or what you're taking the square root of, is not 0, or is less than 0, so it's a negative number. So this is like when you have like the square root of negative 4. So in this case we have this, n is 2, so that's a square root of negative 16. So this is where we have to use imaginary numbers. So whenever your n value is even and your a value, or what you're taking the square root of, is negative, we have to use imaginary numbers, or I. So remember, in that case, the square root of negative 1 is equal to I. So here, what we would do is separate this into square root of negative 1 times the square root of 16. So the square root of 16 is 4, square root of negative 1 is I. So we write that as 4I. Okay. So that's just something to remember for problems like that. All right. And that's where we'll stop. I know there are some other things written here. There are things we've already touched on. So that's your notes for today. That's rational exponents.